Yes, excellent.
Yes.
Over to you, Janet.
Yeah, okay. I'll start sharing my presentation. Let's see. Can you see my presentation?
Nearly. Just wait a moment.
Yeah, okay.
Yes, it's good.
Yes? Okay. I will tell you something about how we try to communicate uncertainties in the newest KNMI climate scenarios. And I will probably also tell a little bit more about my experience with communicating uncertainties related to climate data. As Charlotte said, I work for the Dutch Meteorological Institute, but I also work for the Applied University of Amsterdam as Professor of Climate Literacy. And uncertainty is also one of the aspects that I'm interested in to do some research on. So I was very pleased and willing to give this presentation. As I said, I will tell something about the KNMI 23 scenarios. They were published on the 9th of October, so very recent. And something about visualizing and dealing with uncertainties. But first, something about the KNMI 23 scenarios. I will start with the aims that we use also for the former scenarios. Beside translation of IPCC projections to the Netherlands, one of the main aims is that it makes it easier to deal with uncertainties for the climate change in the Netherlands. And that means that it also has some impact on how we constructed the scenarios. I will tell something about that. But what is very good to realize is that we discussed a lot of these things also with potential users during workshops, surveys, etc., to get an idea whether the way we want to do it links to what the users will need. Okay, this is the main figure of the new KNMI climate scenarios for the Netherlands. It's about the structure. I will not go into detail, but two things that I want to tell about this figure is that we try to distinguish between several uncertainties. And on the left side, in the vertical axis, you see low CO2 emissions and high CO2 emissions. And that axis represents the uncertainties in the socio-economic and technological developments in the future. They are linked to SSPs, as I will show in the next slide, but we use mainly the global temperature rise from these emissions. On the horizontal axis, on the top, you see a drier climate and a wetter climate. And that axis represents the uncertainty about the climate system. And we explicitly made a distinction to also be able to indicate what people can do. I'll show you later. Something more about the structure. We used two SSPs, especially the highest one and one of the lowest ones. So we used SSP 5 8.5 as the one for high CO2 emissions, and SSP 1 2.6 as representative for the low emissions. And there is a middle one in between, but we do not emphasize that much. I will tell later on why. But we did construct also scenarios for SSP 2 4.5. As global temperature rise, we used the temperatures that belong to the black dots on the line. So we used the average temperature rise for the different SSPs that we selected. That means that we did not take into account explicitly climate sensitivity. We had a lot of discussions about that with climate researchers at KNMI, but at the end that would be too complicated. So implicitly you can use that. You can say, well, if the sensitivity is higher, then you could also say the high emission scenario links to SSP 3 7.0, or if the sensitivity is lower than you're at the upper end of SSP 5, 8.5. That is the way how we try to communicate it, but in most cases, users are not interested in climate sensitivity. The information about the high and the low scenario is enough for them to use. Then the uncertainty about the climate system itself. For that, we analyzed many different global climate models, those included in the CMIP6 ensemble. And well, the last 5 years contained many years which were relatively very dry, also in the Netherlands. And for that reason, we saw that there was more interest in drought. So we looked whether we could include that better in the scenarios. And if we compare all the GCM simulations, then we see that there are models where the annual precipitation will increase, but also models where the annual precipitation in the Netherlands, or the area in the top left of the slide, will decrease. And we decided to use that because, well, in all cases, summers will become drier. But if in winter there is a lot of increase in rainfall, then you can supply again the groundwater, etc., with the rainfall in winter. But if the winter rainfall is not that high, you cannot do that, and the impacts of drought in a summer may also be felt in the year after. This is also something that we discussed with the users, because first we had a combination in the former scenarios of very dry summers and very wet winters. That also sometimes occurs in the models, but more in CMIP5. But this new division of the models is more useful, more interesting for the users in the Netherlands. Okay, then another type of uncertainty that we communicate about is the natural variability. On the left side, you see the figure that we used for the former climate scenarios in the Netherlands. And that was to explain the difference between different time scales. So you can have a lot of uncertainty about, or variation, that's a better word in this case, between daily temperatures. But if you look at from a climate perspective, then you want to look at a 30-year period and compare it with another 30-year period. And then the variation becomes much smaller. But that's the left side that we use for the former scenarios. In the new scenarios, we tried a different way of comparing it, of explaining this. And I'm not sure yet whether this works well, works better than the former one. On the right side, you see on the bottom 3 figures. I think those will work well, but the top figure is really complicated, and I think most users will not really understand that. But that is good to evaluate later on. And maybe it's also good to realize that for many people, many users, the year-to-year variation is as important or more important than the natural variability from a climate perspective, so a 30-year to 30-year uncertainty. Another comparison between figures that we used for the former scenarios and the current scenarios. On the left side, you see a figure as we used in our climate dashboard. In this case, it presents the average summer temperature, and you see with the black line the differences between years, and the blue line represents the trend, and then the light blue lines, if you hope you can see them, the horizontal ones, they give the climate normals. We analyzed this. We asked many users, what do you understand this figure? And it appeared that they had a lot of difficulty understanding, especially the horizontal lines, also for the scenarios in the future. And therefore, we tried to develop a different figure, and that is what is presented at the right side, where we only give points and where we use a gray band, which gives the year-to-year variation for the past climate, but also for the future climate. And well, this is understood much better by the users, and that's why we use this by now. Well, I said already that there is a difference between the year-to-year variation and the 30-year to 30-year variation. And for the KNMI 14 scenarios, we had a lot of discussion within KNMI on how to present it. Most of the climate researchers wanted to present the 30-year to 30-year information of variation, because, well, that gives you an idea whether the climate will change significantly. Of course, that's useful, but at the same time, I know from my experience with users that most people can understand the year-to-year variation much better, and that is more relevant for them. You look at agriculture, ecosystems, water management, what is most important for them is the year-to-year variation. And with a lot of effort from my side, we also decided to present some figures with the year-to-year variation. And here they are presented side by side. And I think it's useful to give the users both types of information. Something else that is important for the users is how far you look ahead. For the new scenarios, we decided to present also information for time horizons beyond 2100. In the former scenarios, our farthest time horizon was around 2085, so the last 30 years of the century, and then the middle is 2085. And with the new scenarios, we decided that for the downscaling, we could also present information for 2100 and even 2150, and for the sea level rise scenarios, even up to 2300. Of course, this is much more uncertain, but especially for sea level rise, it's very important to know what will happen afterwards. Dutch water managers and people who do research on this say that, well, up to 2, maybe 3 meters sea level rise in the Netherlands we can manage. But if you reach already 1 meter in 2100, then after 2100, you will reach for sure more than 3 meters. And that is something that people should realize, and it's important to look further ahead. And with these two figures now in the new climate scenarios, one with the scenarios up to 2100 and the others up to 2300, we try to show people that what you do now will have effect on a very long time horizon. This is about biases and impacts. What I also experience is that people do often not realize that time series that come from a climate model can contain biases. And this is very important for the impacts. And if you're not aware of this really well, then you can have an error or uncertainty about what will happen in the future. On the left side, you see that, well, you see what a bias is, a systematic deviation from reality. And you can correct for that by comparing it with observations, the simulations for the past climate. And on the right side, I gave an example of the potential impacts. The dotted lines give the information without bias correction, and the other lines give the information with bias correction. If you have a model that systematically gives too low temperatures, then the potential yields that you can get, for example, for wheat, will be underestimated with the climate model data without bias correction. But with a certain increase in temperature, you may get a certain increase in yields, at least for the Netherlands. But if you use the bias corrected data, then it may be that you get a different change in yields because you get above a certain threshold level above which the yield will increase. And that is what I try to emphasize often, is that if you want to give information on the impacts, well, most impact models do have thresholds, nonlinear relations, etc. And therefore, you do have to bias correct the climate model data to get a good impact assessment. Then something about dealing with uncertainties. But I already distinguish between natural variability, and that is a type of uncertainty that cannot be reduced. You can only quantify it better if you have more observations and more data, and then you do have a better basis for statistics. But the other two types of uncertainties are related to limited knowledge about the socioeconomic and technological developments and about the climate system. That's a lack of knowledge, and you can reduce up to a certain level that uncertainty by doing more research. But in the meantime, what would be a good approach is using scenarios. So if you have the natural variability, then you can use statistics and use probabilities. But in the case of limited knowledge about systems, you do often not have a good basis for probabilities. And in that case, you use scenarios which indicate, well, what if situations without a clear probability. What I also often say to users is that it's important to not only look at the probability. Of course, it's difficult to give a probability, as I just explained, for the climate scenarios. And the most probable scenario is probably not the most relevant scenario. People often do not realize that. If you go, well, many things in society cope with extreme situations. Only in this case, the extreme situation was more extreme than what the sewage system was designed for.
Jeanette?
Yes?
Jeanette? I
Yes?
just interrupt you. You seem to have lost your screen. We can't see your screen anymore. The last image we saw was of the road that was flooded.
Yeah, do you see that? Because I'm now on the slide with probability and relevance.
We don't see your slides just now, no.
Okay, shall I go back for a moment? Do you see now the slide on dealing with uncertainties?
I think maybe your screen has stopped being shared for some reason.
Shall I just stop and then try to?
Yeah, share.
Yes.
Share again, because I think
I will try to.
I think your connection was lost for a few seconds. That's why.
Yeah. Okay. Then I will start sharing again.
Thank you.
Sorry for the inconvenience.
It's really fine.
Yeah. Okay. Do you see my screen again?
We just wait a few moments for it to come through.
Yeah. It's a slightly delay.
There we go. Yes.
Yeah. And it's the slide on probability and relevance.
Yes, it is.
Yeah, okay. So what I often say to users that come to me for advice is that they should look not for the most probable scenario, but what is most relevant for them. And in most cases, that is a scenario that is less probable, but that gives an extreme situation for them. And well, I did that very often, so by now I hardly ever get that question anymore. But it's good that people realize that you can look differently at the scenarios and make a different selection depending on what is most relevant for you. For a sewage system in a city, probably the scenario with the highest increase in extreme rainfall is most relevant. But if you look at, for example, I had a case for the gas company. They have to store gas to have sufficient gas for the winter, for warming the houses. For them, the scenario with the lowest increase in temperature rise is most relevant for them. Okay, then something about the use of scenarios and dealing with it. Well, we developed several scenarios, a set of 4, in this case 6 scenarios, and people often think that still 4 scenarios is a lot to use. So people often want to make a selection. And what I advise often is that if you want to explore the impacts of climate change, then use at least 2 scenarios. Use a scenario with the lowest increase in the variable that is most relevant for you, and the scenario which has the highest increase in the scenario that is most relevant for you. If you want to explore adaptation options, then it's also wise to use at least 2 scenarios. Because if you develop an adaptation strategy for one scenario, you also want to know whether it works well if in the future the climate will be more like another scenario. So is it robust, the adaptation option, and more how to say it? Does it work under different future climate scenarios? Then if you develop policies for adaptation, it can be that you use one scenario to base your options on, but it's good to have the background information about several scenarios. And in the Netherlands, we do have, for example, for the coastal development, they use several scenarios. For the short term, they use a scenario with low sea level rise. For sand depletions, sand depletion on the coast. For the dikes, they use a higher scenario, and in that way, they use the uncertainty and several scenarios. I also sometimes see that people use just one scenario, but I always emphasize that one scenario does not give a complete impression of the range for the future. And in most cases, you will need that to get an idea of the potential impacts for the future, but also for your adaptation options. Then a few examples on communication. If there's no more time, then just indicate it to me. Then I just put some things together to share, but if it takes too much time, then I will skip a few. Okay, what I often see is that only one scenario is presented for the future, because it's a lot of work to make a picture, to analyze all the data. And if you do that, in this case, you see a picture of summer precipitation in the Netherlands, and one scenario for the future. This is for the former scenarios, but it doesn't matter. But this was presented often, and then people have the idea that it will become dry, that it's completely sure. Because the yellow color refers to lower summer precipitation. But in the former scenarios, we also had a few scenarios which had a slight increase in summer precipitation. So just presenting one scenario for the future as I said before, does not give a good impression of what can happen in the future. And it would be better to present this. And you do have two different scenarios for the future and one for the current situation. You don't even have to discuss a lot about the uncertainty, but just by presenting two figures for the future, you implicitly already communicate that there is some uncertainty for the future. Another thing that I experience is that implicitly people often select a middle scenario because they implicitly assume that it is the most likely one and that is best to use. But as I said before, it's difficult to give probabilities to scenarios, and what is the most probable is often not the most relevant. So to stimulate people to think about it, it would be better to give 2 scenarios or 4 scenarios and not really a middle one. As I said at the beginning of the presentation, we also give information in the new scenarios for SSP2 4.5, but we did not give that much attention to it because otherwise we know that people only use that scenario and do not look at the other scenarios anymore. And well, that is not what is most useful, I think, for the people who have to think about adaptation options. But visualizing information is also can also give different interpretations. On the left side, you see something about the relative importance of the different types of uncertainties. So natural variation, uncertainties due to socioeconomic developments, and uncertainties due to on the climate system. But if you present the right figure, then you get a complete different interpretation or picture of the importance. And with new scenarios, I now also emphasize more that the uncertainty about the future climate around the end of this century is not due to especially the uncertainty about the climate system itself, but it's especially due to uncertainty about the socioeconomic development. And with the figure on the left side, you can explain that more easy, I think, than on the left side. Also some experience with the wording that is used. Uncertainty is a word that is often interpreted differently by many people. It depends on who you're talking with, but for some people, uncertainty means ignorance. But in itself, the types of uncertainties sometimes refer to lack of knowledge, but it's also interpreted differently by people that they say, well, you do not know much about, you do not know at all something about a system. So often it's better to use the term range, or if you have to use the term uncertainty, explain clearly what you mean with it. Well, there's some other examples in this document, and for me that was really interesting to see how people could interpret the words. There's another example. What I experienced is that, but this is from a website where we present information for different locations in the Netherlands on climate change. And people often like to have information for a location close to their own house or where they work, because that's more appealing to them. And depending on which location, you can get a different impression. If you look at Vlissingen on the left side, you see that for 2050, the number of tropical days, so above 30 degrees, increases from 3 to 7 days, from 1 day to 3 or up to 7 days. And if you look at a location more in the middle of the country, it changes from 5 days to 8 to 14 days. So the percentage change is different. It's much higher for Vlissingen than for Delen. And if you present your information in percentages, then people often assume that the percentage is valid for the whole country. But for these kind of indicators, that is not the case. Something else that there are also, what I often see is that with climate science, the uncertainties are often emphasized, whereas it would be better to do it the other way around. You could say, well, there are many uncertainties about climate change, but we know that temperatures will change. Or you can say all climate scenarios show temperatures and will increase, even though there are some uncertainties. The last message is more appealing to many people, therefore it's more, well, it's probably better to use that. We should, I think, not emphasize the uncertainties too much, because some people are more paralyzed on that. They think, well, it's too huge, the uncertainties, so I will wait until they know more about it. But if you phrase it in a different way, then people have the feeling that, well, they can manage that. On the other hand, we should not obscure the uncertainties, but only mention them when it's really relevant. Okay, that's it.
Thank you very much, Janet.
Yeah.
It's a fascinating discussion, presentation.
Okay.
Thank you
Okay.
so very much. We do have a couple of minutes, and there are some questions that have appeared in the chat specifically for you.
Okay.
One of them is from Jerome Sevonat. He asks, if I'm correct, you use natural variability instead of internal variability, and can you explain why?
Yeah, you could use both terms. Yeah, I often say natural variability. Maybe sometimes better to use internal variability.
Okay, so thanks again for the presentation.
Yeah.
Really
Yeah.
interesting. So there is no strong point. I mean, it's not a question of getting the users, the non-climatologists, to understand it better.
No, I think that then maybe the term natural variability will be easier for them to understand than internal variability.
Right. Okay.
But I don't think it matters that much. What I often do is also explain a little bit why we do have that natural or internal variability.
Right.
And then I use an example as, for example, in the Netherlands in summer, when it's really hot, then there's often a wind from the south or the east that transports warm and dry air from the eastern or southern Europe. And many people think, oh yes, I know that. And well, a similar subject I have for the winter, for example.
Right. Okay, thank you.
Yes, thank you, Janet. I'm going to see if Andreas is here now. Andreas is joining us a little bit after the beginning of the meeting because he had a previous
Here,
meeting
can
he
you
was
hear me?
attending. I can hear you, Andreas. Yes.
Yes, good.
Great. So Andreas is here from DNV, and we've invited Andreas to speak because he has some experience about conveying uncertainty in terms of risk assessment. So over to you, Andreas.
Thank you. I'm just trying to share my screen.
Brilliant.
Is your question about see something. Wouldn't you achieve more acceptance by the users if you use a realistic scenario?
Ah. I will put that one into the document to discuss during our panel discussion.
Okay.
Okay. Can I start?
Yes,
and can
please
you see
go
my
ahead.
screen?
We can indeed.
Yes, good. So my name is Andreas Haver. I work at the DNV. I'm a researcher. I have a background from physics, but in DNV I've been working for almost 10 years now with risk management, trying to improve the methods we use for doing risk assessment in different industries. And so that is my sort of background. And trying to change the slide. Yeah, now it works. So my goal for this talk is to connect the concept of risk and uncertainty and discuss how to describe risk and uncertainty. But my point of departure is the kind of work that we have done, which is more like doing risk assessment for industry. For example, energy industry, maritime industry, where you have some kind of potential for major accidents and you want to assess the risk. That's sort of where I'm coming from. More recently, we're also working with risk related to artificial intelligence and a little bit with climate risk. So that is sort of my point of departure. First question I ask is, how can we define risk? Because risk is something that all of us talk about and you sort of take it for granted that everyone knows what risk is. But how can we really define it? If you look at the Cambridge Dictionary, it says that risk is the possibility of something bad happening. If you look at what the IPCC is saying, they say that risk is the potential for adverse consequences. I think they added a little bit to that, but that's basically the core of the definition. You look at ISO 31000, which is the major risk management ISO standard. It says that risk is the effect of uncertainty on objectives. And then there's the standard called ISC 61508, which is used in a lot of process industries for safety functions. And they say that risk is the combination of probability of occurrence of harm and the severity of that harm. So there's so many different definitions. If you go to the Society for Risk Analysis, you would expect that they have a clear definition of what risk is, but they actually have no consensus on the definition, but several alternatives. For example, that risk is the possibility of an unfortunate occurrence, or risk is the potential for realization of unwanted negative consequences of an event. I'm not going to go through all of them, but my point is just to say that there is not sort of a consensus on the definition of risk. We asked in the Climate Europe Webstival in September, first of all, have you heard about this ISO 31000 risk management standard? And most people had not heard about it. When we asked about the preferred risk definition, nobody answered that they preferred the one from ISO 31000, which is effective uncertainty on objectives. The ones that were most preferred was the likelihood times impact and consequences with associated uncertainty. And when we asked what do you see as the challenges of applying this ISO 31000 definition, the top answer was that the term uncertainty is hard to operationalize. But also that it's hard to use the definition to qualify and rank risks. So I'll try to sort of address this a little bit in this talk. So since risk is something that all of us talk about and sort of have an intuition about, I asked myself, what does risk feel like? So imagine that you need to make a decision. For example, myself, I recently bought a house. I know that there are certain consequences, certain unwanted consequences. Like there are certain things I like about the house. There are certain unwanted consequences, like the price. I don't want to pay too much. Some of the consequences are certain and foreseen, like I know the area a little bit, but I don't know if I'm going to like it. There's certain things that are uncertain and unforeseen. So you have this space of wanted, unwanted, certain and uncertain that you have to navigate. In everyday life, we face a lot of such decisions. You have, for example, to decide how to travel. Should I take a bus? Should I fly? Should I take the train? Buying a house, like I just mentioned, selecting a partner, accepting or deciding a job offer. In all of these situations, you have some consequences that you want, some consequences you want to avoid. Some of them are certain or foreseeable. Some of them are uncertain or unforeseeable. And you are navigating this space and weighing things up against each other. But this the feeling of risk is different for different people. Because people have different objectives, like what they prefer and what they want and what they want to avoid is different. But also they have different knowledge and different ways of knowing. But relating back to these definitions I showed earlier, I've highlighted in blue and green, like the one dimension about uncertainty from the ISO definition, or potential from the IPCC definition, is the one dimension. And the objectives or adverse consequences is the other direction. Has to do with unwanted and wanted consequences. So this is sort of my intuition about risk, to look at it from a decision perspective. In this decision, what is at stake, and what is it that I know and what is it that I don't know. But this begs the question, what is uncertainty? Again, you can look at a lot of definitions. There was one definition from a book that is used a lot in engineering, reliability engineering. It says that uncertainty is that which disappears when we become certain. Or the Cambridge Dictionary, a situation in which something is not known, or something that is not known or certain. Or the Society of Risk Analysis, imperfect or incomplete information and knowledge about a hypothesis, a quantity, or the occurrence of an event. And then this other one that I found in a paper, any deviation from the unachievable ideal of completely deterministic knowledge of the relevant system. So now you see all of these, they relate uncertainty to knowledge. So that begs the question then, what is knowledge and how is it related to knowledge? It's common to divide knowledge into three types. Propositional knowledge. Sorry. So for example, Oslo is the capital of Norway. It's like a fact, or it's a statement, proposition. They also have know-how, for example, knowing how to ride a bike, or familiarity or acquaintance knowledge, like knowing the taste of bananas, for example. Often when we do risk assessment, it's about propositions. So like the consequence of X will be Y. And importantly, you can only then be uncertain about propositions that has a truth condition, something that can be observed to either be true or false. But we can also be uncertain about know-how and familiarity or acquaintance knowledge. So, for example, we might misidentify something, or be uncertain or mistaken about how to do something. And all of this is part of the uncertainty that goes into risk. There are a lot of ways of categorizing different types of uncertainty. And I like this figure from a paper from 2003 by Warren Walker et al. Defining uncertainty, a conceptual basis for uncertainty management in model-based decision support. It's a very nice paper. They propose to sort of categorize the different ways of categorizing uncertainty according to location, nature, and level. So location is like where in the sort of the modeling pipeline, so to say. Like, is it the context, the model, itself, like the model structure, the inputs, the parameters, the output. Where is this sort of uncertainty located? The nature of the uncertainty is the, on the one hand, aleatoric or variability uncertainty, actual variation in the world, or the epistemic uncertainty, which is like lack of knowledge. And then the level is a range from complete determinism to total ignorance. And I think this is quite a nice way of dividing the categorizing uncertainty according to different sort of different aspects. So how can we describe risk? Usually when we in DNV do risk assessment, we present some risk metrics. We make plots of risk, like we show risk matrices. You have likelihood on one dimension and severity on another. Sometimes you plot a risk map, like you have different colors for risk at different locations. Let's say it was a flood risk or something like that. Sometimes we provide these risk radars where you sort of show how different, let's say, different solutions or different scenarios or something score on different parameters. You can have many different dimensions that you can show in this way on this kind of radar plot. Or you use something called an exceedance curve, where you plot the frequency of some event of a certain impact, let's say frequency of floods of certain magnitude. And sometimes you just give forecasts of some quantity of interest with uncertainty around the predictions, and maybe with some critical limit, and you can show sort of uncertainty about when this limit will be reached. But these are all quantitative ways of displaying risk. But risk is more than what we can quantify with metrics, because any risk assessment involves choices and assumptions along the way. So the first thing you do when you do a risk assessment is that so first of all, the risk that you want to describe is the consequences and associated uncertainty, if we just take that definition as a starting point. First thing you do is that you define a scope for your risk assessment. Which consequences are you considering in the risk assessment? And then you're interested in the uncertainty about those. So for example, in the context of climate risk, it could be that you're focusing on, let's say, risk of flooding, for example. So that is the scope, and you're ignoring other things that may also be a climate-related risk, but it's outside of the scope of your assessment. Then when you have decided on the scope, you choose some models. Often it is probabilistic models of the consequences of interest, including some kind of representation and description of the uncertainty. So you do your modeling, but then in the end, what you typically do is that you summarize the findings of those models in some kind of metrics and visualizations. So what this figure is trying to show is that the metrics that you present, like the examples I showed on the previous page, they may capture aspects of the risk, but not the full risk picture. An important part of the risk assessment is to identify the assumptions that may hide risk. So it's sort of the risk that you can see that is captured by the metrics, but then there's also the hidden part that you don't see. And often a major part of the risk could be in that hidden part. And that's very important to be aware of. The challenge is that many assumptions are tacit and not explicit. It's difficult to actually know that you made assumptions. One way to expose such assumptions is through a method called assumption deviation risk method, basically assessing three aspects of these risk metrics. So how sensitive is your conclusion of the risk metric with respect to the assumptions? What is your belief in or the possibility of deviation from or violations of those assumptions? And what is the strength of knowledge supporting the assumptions? And then you can come up with different settings from critical to not critical. And if it's not critical, basically means, okay, you can just use these assumptions and sort of your metric is representative. It doesn't really critically depend on these assumptions. To the settings 5 and 6, where really you cannot put much trust into your quantitative metrics. This is from a paper by Roger Flage, who's a researcher at the University of Stavanger, professor of risk management. So when you describe risk, to get a more complete risk picture, you should not only use metrics, but you should also include some evaluation of the knowledge bases. So for the metrics, it's common to use some probabilistic metrics, but sometimes also something like interval probabilities, other methods like Dempster-Shafer or subjective logic. But you also need to do some qualitative description of risk, like describing the rationale, evidence properties, the degree of consensus, as I mentioned, the criticality of assumptions, and maybe the location and nature and degree of uncertainty. That's also very relevant information to provide when you are communicating risk. And some people, especially engineers, may ask, but can we not just quantify everything? Like, can we not just put a distribution on the uncertain parameters? Or maybe we can use interval probabilities instead of probabilities to say, okay, I'm not exactly sure what the probability is, but it's in this range. Or there's something called Dempster-Shafer or subjective logic, which are methods where you actually, instead of just assigning probabilities, you also have this third or second dimension of uncertainty. Like, you can assign the same probability value, but sometimes you're more certain about it than others. So you have this extra dimension. Without going into details about that, in any case, you need to make some qualitative evaluations in the end. Give some kind of reason, why did I end up giving that probability or that probability interval? So you cannot get away from doing some qualitative assessments. So the question is, when is it useful to be quantitative? Here's a figure from a paper from 2017 showing how this is done in what the IPCC recommend that you do in the context of climate risk. So you first look at what evidence exists, evaluate that evidence, and if there's a sufficient quality and agree to evaluate confidence, then you evaluate confidence. And then only when the confidence is sufficiently high, then you go and use probabilistic and provide likelihood estimates. So basically, depending on the sort of strength of the knowledge bases you have, you decide how quantitative you can be. Another way to show this is that the risk description needed should match what is supported by your knowledge. Sometimes to make a decision, it's okay to just be qualitative. So even if you can do a quantitative analysis, it may not be necessary to come to your conclusion. Other times you may need something more precise. So this figure is just trying to show that ideally there should be a match. You don't need to go into too much detail, but also you shouldn't provide, it can be misleading to provide very detailed numbers when your knowledge basis doesn't really support it. So to conclude, risk is about consequences and uncertainties in a decision context. That is how it feels like for me. And if you look at the different decisions, they all somehow mention these aspects of consequences and uncertainties. But the definition of risk is not the same as the definition of risk. So when we actually describe risk, we usually use this kind of metrics that capture certain aspects of the risk, but not all of it. So it's very important to be aware of all the assumptions that you make, and that part of the risk is hidden. But still, the major part of the risk may be the hidden part. So by just looking at the visible parts, the metrics that are provided, you may miss the actual, the big risk. The assumptions are sometimes tacit, so you don't really know that you have, or it's not explicit that you made the assumption, so that can be dangerous because then you miss the hidden risk. And then it's not always necessary to be quantitative because often people like to put numbers on things because it's easy to compare numbers. If you want to rank something, you want to have numbers. But it can be sometimes misleading if those numbers are not well founded on the knowledge that you have. So it's important that you can match that the needs in the decision context matches what the knowledge can support. Yeah, thank you for your attention. Any questions?
Thank you, Andreas. I was interested to see that some of what you've been talking about in terms of the scope of what you're interested in reflects quite in a parallel way to what Jeanette was talking about in the presentation before you, in terms of being aware of what is the relevant climate metric for the situation that you're advising on. And it seems to be, very interesting to see that those two things align. So I have a question which is to do with the tacit risk, the things that you don't realize that you have made assumptions about. But I also know, so if you can tell us a bit more about how we might reveal that, that would be great. But also I see that Jeanette has raised her hand. So
yeah, and had a similar question on what kind of assumptions you well you came along.
I think part of identifying tacit assumption is to have some kind of structure to know where to look for assumptions. So this figure is just a sort of a first rough sort of picture of where the assumptions can enter. So the first place they can enter is when you define your scope. And then it enters more assumptions when you choose how to do the assessment within that scope. And again, when you present your results. So this is just sort of helping you to identify where the assumptions enter. And there are some frameworks used in risk assessment to sort of try to come up with assumptions. So kind of guiding people to realize their assumptions. I'm not familiar with how this is done in climate risk. But I think just having some kind of understanding of where the assumptions can occur and a systematic way of going through and checking, may I have made an assumption here? And is it, how certain is it? I think that can be very helpful.
What I often do is ask people why they need certain information, how they use now information about climate change, how they want to use the information, what kind of models, etc. they use. So I think this touches upon the things that you also presented in this slide.
There's also a question from Roger Street in the chat.
Charlotte, you're muted.
You're muted, Charlotte.
A schoolgirl error, I apologize. So Roger Street asks in the chat, is this also reflecting that for risk assessments, we also need to accept continuous learning and improvements?
Of course. As I mentioned, risk is subjective. It depends on the knowledge you have, and of course knowledge increases, or hopefully some knowledge also actually deteriorates, but knowledge changes over time, so it is continuous. Even the scope may change, the kind of things we focus on, and our values and objectives change over time. So something that was considered a risk, or something that was not considered a risk, suddenly is a risk that we consider. So yes, it's very much about continuous learning.
And to follow up on that, as we evolve what we consider to be a risk, is there a danger maybe that we lose, people lose faith in what we're telling them when we change our mind about things? How do we keep the confidence of people as we evolve our understanding of risk?
That's a good question. When I worked with this, it's been mostly in the context of like industrial risk assessment, where you have kind of a, let's say, industrial plant or oil platform or something, where you sort of, you have certain things that is agreed that this is what we're concerned about. But of course, over time, you realize maybe the environmental impact, for example, is much bigger than you thought. And so you change your focus. Like, so it's more in an industrial context, but what you're asking is more sort of, how should I say, personal experience or views on what is risk and what's important. I don't think I have a good answer, but just being clear in your communication and sort of what is my scope is important.
In the chat, Asun asks if you can say something about the communication of risk and uncertainty in the context of climate change.
Yes, so climate change is not my domain of expertise, but one thing I could say is that uncertainty is part of the risk. And often when I hear people talk about climate risk, uncertainty is sort of seen as something that is used to take risk less seriously. Like, okay, because there's uncertainty about the models, for example, there's uncertainty in the data, people sort of take that to mean that that the risk is lower. Whereas the way that may be interpreted is more that actually, uncertainty is part of the risk. So actually more uncertainty is actually a reason to take it more seriously. And this is something I think, not taking uncertainty to be something bad, but actually something that is a useful guide, that you need to be more cautious when you have more uncertainty. Not try to shy away from uncertainty, but I only heard the last part of the previous talk, and I think it's a little bit different from the message there, that people don't like to hear about uncertainty. We actually experience the same when we work with the risk assessment for industry. They don't like to hear about uncertainties. They want to just get numbers and clear recommendations. But I think it's possible to turn uncertainty into confidence, that you are more aware of the assumptions you make and how those assumptions can affect your conclusions. Then you can be sort of more confident about the decision you make based on the risk assessment. So I wouldn't sort of shy away from the uncertainty. I would try to use it to guide and sort of try to turn it into confidence. Because there's a lot of things you can say despite uncertainty. For example, the example that was given earlier, despite uncertainty, it's quite clear that temperature is rising. You're actually using the uncertainty to turn it into confidence. But I don't know if that answered Asun's question, if that is what she...
It's certainly been food for thought for us. So just one final comment from Roger Street. He talked about assumptions embedded within the decision support systems, in which knowledge and data are being used, and that this may also need to improve risk assessments.
Yes.
Roger, if you're here, would you like to unmute and maybe clarify what you mean?
Yeah, the uncertainties that, what I was getting at there is that the uncertainties that exist in the data and knowledge are very important, but there is considerable uncertainty embedded within the decision support systems in which that knowledge and data are being used. So it's trying to understand where what those uncertainties are. And my experience suggests that a lot of the risk assessment approaches that we currently are using may need to be improved as we better understand the way that the knowledge and data is being used and what they're trying to get at in terms of I don't want to, I'm hesitating because I don't want to use the word the answers, but the decisions.
Mhm.
And I think I'm a firm believer that a lot of the risk assessment approaches that we're using need to be improved considerably. And in order to deal with the nature of the problem that we have in front of us, they are very useful in some cases, but very unhelpful and can lead to misinformation or decisions not being made with an understanding of a fuller understanding. I was going to use the word full, but fuller understanding of the uncertainties and risks that the people are trying to get at. Anyways, that's what I was trying to get at there is that many decision support systems, when you really looked at them, are, there's considerable uncertainty in the systems, in the procedures, not the data and knowledge. And but therefore, I think we need to look at also the risk assessment process or procedures that we're using to start to improve them to deal with those and other uncertain and to improve the decision-making process. Hopefully that's helpful.
Yeah, it really is. I'm going to leave the discussion there for the moment because we're about to go into a break. But I noticed that Christopher Jack, our next speaker, has said agreed in the chat. So I suggest we pause here and reconvene at 11 o'clock for Christopher's presentation, and we'll take up this topic some more in our panel discussion. Reconvening at 11 for those of you in Central European time, and at 10 o'clock for those of us in Greenwich Mean Time or Universal Standard Time. So thank you very much to all of our speakers. It's been great so far, Andreas and Jeanette, and I look forward to speaking later. So yeah.